Hello everyone and welcome to this week's Seds Online webinar. We're really pleased to be able to offer all of these resources and opportunities for free thanks to sponsorship from the International Association of Sedimentologists. So this week we're really pleased to be able to welcome Dr. Megan Baker. She completed a master's degree in applied marine geoscience at Bangor University in 2015 before going on to complete the PhD. Her thesis was titled The Role of Clay Minerals on Sediment Gravity Flow Dynamics in Deposits, and she completed that at Bangor University in 2019. In 2018, she was awarded the esteemed Richard Fast Research Prize, which is awarded by the International Association of Sedimentologists to recognise outstanding work in the field of fine-grained marine sedimentology. She is presently a NERC-funded postdoctoral research associate at Durham University and is looking to understand the controls on sediment gravity flows and their deposits, which she's going to be telling us about today. So without further ado, I'll hand over to you, Meg.
Thanks very much, Catherine, for that nice introduction, and thanks to the Seds Online team for the opportunity to present our research. I'm going to be talking today about mixed sand-mud bedforms that we found in the fringe of the submarine fan. And this is work I completed in collaboration with my PhD supervisor, Jaco Bass, when I was at Bangor University. And I should also thank the MSc students who are named just above the photo for braving wet and windy mid-Wales to help us with our fieldwork. So the rationale behind this research, I don't think I need to spend long for this audience to tell you that bedforms are an important topic to study. Bedforms are really great because they can help us reconstruct sedimentary processes, both in the modern environment and in the ancient environment. They can tell us really vital things like the flow direction, the flow strength, and the depositional environment. And because they're so useful, lots of studies have investigated bedform development. And the majority of these studies have focused on bedform development and stability in cohesionless sediment, so sand. But if we look at this diagram on the bottom of the slide, this shows that actually cohesive mud is one of the most common sediment types. And this is true both for the modern ocean and in oceans of the geological past. The figure shows surface seabed sediment samples from all around the globe. And you can see a dominance of dark green dots and light green dots, which signify mud-rich sediments and sand mud sediments. And this high amount of mud in the natural environment is actually really important because we know that clay sediment, which is within mud, has been shown to be significant in bedform development. So laboratory experiments have shown that bedforms that contain mud have different shapes and sizes to those composed of pure sand and can often develop slower compared to those of pure sand. So we want to try and improve our understanding of what mixed sand-mud bedforms look like, how diverse they are. And one environment where you would think, oh, I think there might be quite a few mixed sand-mud bedforms is in the fringe of fine-grained deep marine systems, because these are environments where you have a lot of deposits from muddy flows. And we already know that the fringe of mud-rich systems actually contains really complex deposits, such as hybrid event beds, like the one shown in the photograph below, and transitional flow deposits. And the complexity of these deposits is attributed to the presence of clay changing the flow dynamics of sediment gravity flows. So the question we wanted to ask was, well, what do the bedforms look like in this environment? So to try and understand how or what mixed sand-mud bedforms deposited by clay-rich cohesive sediment gravity flows look like, the first kind of question to address is, well, how does clay change the fluid dynamics of sediment gravity flows? And I tried to summarize that in this diagram here. The first thing to say is that clay is fundamentally different to larger non-cohesive particles. And this is because when it is dispersed in water, it has a surface charge. And this surface charge allows clay molecules to collide and flocculate, and that can start to change the dynamics of the flow. So if we start on this diagram in the top box, in the dispersed clay, this is a situation maybe where we have a very low concentration of clay within our sediment gravity flow. And this means that the clay minerals can't really don't really have the opportunity to collide or flocculate. So in this flow, we would expect turbulent forces to dominate and for the flow to be very well mixed. If we start to increase our clay concentration, the clay minerals have a higher chance of colliding and flocculating. This allows clay flocks to form, and this can increase the yield strength and the viscosity of the flow, and can actually start to modulate turbulence within the flow. So that's the middle box. If we further increase the clay concentration, we can get to the stage where we have a clay gel. This is where we have a pervasive network of clay minerals, and this can make the flow really strong and really cohesive, and can actually completely suppress any turbulent forces we might find within a sediment gravity flow. The important thing with this diagram is that sediment gravity flows are dynamic systems, and they react to changing boundary conditions. So we can move up and down this diagram. So if we were in the stage where our flow was behaving as a clay gel, so it was very thick, it was very cohesive, but the flow started to accelerate, maybe due to a change in gradient, the turbulent forces could start to break up those clay gels, and we could move back up through flocculated clay to dispersed clay. Another way to move back down this diagram is actually not to necessarily increase the clay concentration, but just to slow the flow down. Clay suspensions are shear thinning, and when we slow the flow down, the clay minerals, the flow might reduce as well, but the clay minerals have a better chance of colliding and flocculating and increasing the cohesive forces. And I'm just going to show you some screen grabs of some lab experiments which really nicely show us moving from the top to the bottom of the diagram in the previous slide, so showing flows becoming more cohesive. I really wanted to show you some videos of these flows, but the technology said no. But if anyone wants to have some videos, please send me an email and I'd be happy to send them across. So what do these screen grabs show? These are sediment gravity flows in the lab, and they're composed of different percentages of clay minerals shown at the top. So we start from 1% and move all the way up to 20% volume concentration. And the clay minerals within these flows is bentonite or sodium montmorillonite. So this is really cohesive clay. And at low concentrations, so from 1 to about 10%, you can see that the flows look like they're really mixing quite a lot. They're quite turbulent. So here we're in kind of the dispersed clay section of the previous diagram. The clay minerals aren't really able to change the fluid dynamics that much. When we increase the clay concentration up to 16%, the bottom left figure, you can see that we really start to change the flow behavior. So it looks like we have a dense lower layer, and at the top, a layer where we can see more mixing with the ambient fluid. And this is where clay minerals have been able to start changing the flow dynamics. So they've been able to collide and flocculate and increase the yield stress of the flows. What I should say is that above 16%, we saw a significant reduction in the mobility of the flows. So as we further increased the clay concentration, the flows travelled shorter and shorter distances from the point of release. As we further increase the clay concentration as well, we see big changes in flow behaviour. The 19% bentonite flow, you can see, is a very dense layer, and there's hardly any mixing with the upper surface. So this flow is really strong, it's really cohesive. And then at the very far end of our set of experiments, the 20% bentonite was basically a slump. So here the clay cohesive forces had increased so much that the flow barely left the reservoir. So those were some nice kind of visual images of these kind of clay modulated flows. Other experiments have done some really nice work where they've looked in detail at the kind of velocity structures we see within these different types of flows. And they've produced flow classification schemes categorizing this continuum of flow behavior. And these images here are kind of schematic diagrams of the flow classification scheme by Bass et al. In 2009. So if we move through these images from 1 to 5, we are increasing the cohesive forces. So for number 1, we have a turbulent flow, and the kind of turbulence is portrayed by the kind of size and strength of the swirls. So number 1 is a turbulent flow, it's fully mixed. Oh, and also I should have said before I started that, these are open channel flows or open channel experiments. So you might be thinking, why don't I see the mixing at the top of the flow? That's why. As we further increase our clay concentration to go to number 2 and 3, we produce turbulence enhanced transitional flows and lower transitional plug flows. These flows are actually really interesting because we increase the cohesive forces, but we also increase the turbulence near the bed, which might seem a bit counterintuitive. The reason why we have increased turbulence near the bed is because we've started to develop a laminar plug. You can see that developing at the top of number 3, and kind of the lines in number 2 denote that. This laminar plug actually makes an extra shear layer within the flow, which enhances turbulence near the bed. Further increasing the clay concentration takes us to number 4, which is an upper transitional plug flow. Here, the plug has really moved down in the flow, and we've actually started to really reduce the turbulence at the base of the flow. And you can see that by the smaller swirls. Number 5, we have a quasi-laminar plug flow. So this is where we have a lot of clay in the flow, and you can see it is pretty much almost all a plug layer, and there is very reduced turbulence near the bed. And this is the same as a debris flow. So you can see that we have a big change in fluid dynamics as we increase clay concentration within the flow. But we're interested in the bed forms which are produced by these transitional flows. So what do they look like? Well, actually, what's really nice is that there's already been some laboratory experiments which have investigated the sediment structures produced by different decelerating transitional flows. And this work identified a number of mixed sand mud bed forms. The top picture and kind of schematic beneath show large current ripples. These are bed forms which have greater heights and longer lengths than normal sandy current ripples. The bottom photograph and schematic show low amplitude bed waves. And these are bed forms which, as the name suggests, have very small height and really long lengths. So the question I wanted to ask was, well, can these bed forms be found in the field? And maybe at the start of the presentation, I made it sound like we didn't really know, and it was quite intrepid. But actually, we already had a really good idea of what we were looking for due to these really nice laboratory experiments. So we decided to conduct field work in the mud-rich submarine system that makes up the Aberystwyth grits group and the Borth Mudstone formation. The photograph on the right shows a kind of zoomed out image of the outcrop. And just to start getting your eye in, you can already see the kind of sandy beds, which are a lighter grey and they're sticking out a bit more, and the mud-rich beds, which are a darker grey. We find these outcrops in mid-Wales, and they're coastal outcrops. And the rocks are early Silurian in age, and it's thought that sediment gravity flows came into the basin from the southwest, and they were deposited in an elongate sub-basin which was bound by northeast striking normal faults. So this is a confined system. What's really nice is that the paleo flow is to the northeast, which is along the cliff line. So just a little bit more detail about the rocks. If we focus first on the bottom right graph, B, this shows the texture of the logs we took from the proximal part of the system to the very distal fringe. And we can see that the amount of sandstone in light grey reduces and the amount of mudstone increases, which is what you would expect. We actually focused on really the very distal part of the system. So that's shown in the red box. In A, we looked at the rocks between Aberystwyth and Borth. So we were looking at the very distal part of the Aberystwyth grits group, which you can find from Aberystwyth to Harp Rock. And I've included a photo of Harp Rock in the sunshine, because I think that's an amazing structure as well. And then we also looked at the rocks in the more proximal part of the Borth Mudstone formation, which is from Harp Rock to Borth. Within our study area, we defined 2 sub-environments following work by Prelat and Spatial. And we defined the fringe of the system and the distal fringe. We said the fringe is the area where in our logs we have a mud content of roughly 70%. The distal fringe is distal of the fringe and is an area where we have a mud content of about 90%. So I'll start using those terms quite a lot now. So the methods we used, I won't spend long on this because it wasn't anything out of the ordinary. We took sedimentary logs all through the system, or all through our study area, I should say. And then we did Markov chain analysis to look at the common facies transitions to make facies associations. The results I'll mainly show you today are the detailed descriptions we made of all the current generated bed forms we could see. So between Aberystwyth and Borth, we just walked along the outcrop, and every time we saw a bed form, we would stop. And you can see the photograph of us there looking and thinking about them. And for each bed form, we'd take photographs, we'd do detailed field drawings, take grain size data, and then we'd also measure the bed form height and length. And so between Aberystwyth and Borth, within our study area, we found 99 locations where we found mixed sandstone mudstone bed forms, and 59 locations where we found sandstone bed forms. Diving into the results, I'm just going to very briefly show you some of our sedimentary logs. These are kind of some representative slices of the sedimentary logs we took. And I should say, sorry, the scale is 1 metre. So moving from A to D, we're moving from proximal to distal, which you can see in the summary figure on the right-hand side. And you can clearly see that we see a reduction in the sandstone, the massive sandstone and the structured sandstone beds, and we start to see the dominance of mudstone beds. So now focusing on the bed forms we found, we identified 3 different bed form types based on shape, texture, size, and internal stratification. And I'm just going to go through those 3 bed forms now. So the first type of bed form we found is kind of what we call the classic sandy current ripples. And we compare these to the mixed sand mud bed forms we found as well. So these sandy current ripples were sort of what you would expect, especially in height and length. So the average height of the bed forms was 11 millimeters, and the average length was 141 millimeters. And this falls in the expected size for sandy current ripples. The ripples had nice asymmetric shapes and lovely cross lamination, and were mostly, well, they were composed of clean sandstone. The first type of mixed sand mud bed forms we've called large current ripples. So these ripples contain mixed sandstone mudstone. And here are some representative photographs of the bed forms, just for you to kind of see the variety of style these large current ripples had. So in A, you can see that this bed form, it has a muddy base, and you can see it coarsening upwards to sand as it kind of gets lighter. Both A and B are climbing, and lots of the large current ripples we saw were climbing, which is really nice because then we could see the full ripple profile. We often also found the bed forms had muddy fronts, and that would coarsen upstream to sand. You can see that in B, and that actually made the front of the bed form kind of really hard to find in a way, and that's why the white arrows are there trying to show where we think the front of the bed form is. In C, you can see a large current ripple that is loaded into the bed below. And these bed forms had sharp high crests and nearly linear 2-dimensional crest lines when we saw them on the bedding plane. What's really critical about these large current ripples, in addition to how they looked kind of from a textural point of view, is their size. So the average height of the large current ripples was 19 millimeters, and the average length was 274 millimeters. So you can see that that is much larger than the sandy current ripples we found in the field. Here's a schematic diagram. I was saying to Catherine at the start of this presentation, I think this is my favorite large current ripple of the system. There's really beautiful structures you can see there. You can see the muddy front, which kind of coarsens upwards to sand. I don't know if you can see it very clearly, but there is some nice high angle cross lamination at the front of the bed forms, which is shown in the detailed picture below. And we can also see nice mudstone drapes covering these bed forms. The final bed form we found in the field, we termed low amplitude bed waves, which follows previous work which have identified these bed forms before. The dimensions of these low amplitude bed waves were really very different. So these had an average height of 10 millimeters, and an average length of 354 millimeters. So they were extremely short, but very, very long. These bed forms were often composed of mixed sandstone mudstone, but occasionally we found ones that were clean sandstone as well. The top image, you can hopefully see the really nice low angle cross lamination in this bed form, about 12 degrees. The bedforms, again, similar to the large current ripples, we often found low amplitude bed waves that were climbing. And again, we also often found that these bedforms had a muddy base or a muddy front, and that would coarsen upwards or upstream to sand. The bottom image shows a sandy bedform, or a sandy low amplitude bed wave, I should say, isolated within a mudstone. So we often found this kind of structure with the bedforms isolated in mudstone, giving a really lenticular appearance. So this plot shows the different bedform heights and lengths for the bedforms we saw in the field. The dotted line shows the aspect ratio, so that's the bedform height divided by the bedform length. And the black box shows the size we would expect for equilibrium and non-equilibrium clear water ripples over the entire grain size range. So we can immediately see here that our different bedform types actually segregate really nicely. So the sandy current ripples in pink, we see in kind of the bottom left, and they actually fit quite nicely within the box of what sandy ripples should be according to bedform predictors. The large current ripples are clearly much higher and longer than the sandy current ripples. And they have aspect ratios of about 0.05 to 0.1. We can compare these aspect ratios to those of the low amplitude bed waves. So the low amplitude bed waves kind of have similar heights maybe to the sandy current ripples, but they have much longer lengths. And this really changes the aspect ratio, which is from between 0.0125 to 0.05. So we can really see a difference in the dimensions between these different bedform types. Another interesting question we wanted to try and answer is, what is the distribution of these bedforms? Are they kind of the same throughout our study site, or do we see any changes? So this figure here shows the studied part of the system from Aberystwyth in the proximal part of our study area to Borth, which was the most distal part. Each dot represents a bedform, and then the pie charts are summaries of 4 sections throughout the outcrop. So we can see that in the proximal part of the study area between Aberystwyth and Clarack Bay, sandy current ripples in pink really dominate. But there are still examples of low amplitude bed waves and a few examples of large current ripples. Between Clarack Bay and Wallog, we see a bit of a shift. We see more large current ripples, more low amplitude bed waves, and a reduction in the sandy current ripples. Our third section, between Wallog and Borth, or kind of between Wallog and the halfway point between Rock and Borth, it's similar in that we again see large current ripples dominating, but still examples of low amplitude bed waves and sandy current ripples. And then finally, and quite interestingly, at Borth, we don't see any examples of sandy current ripples, and low amplitude bed waves dominate, with some examples of large current ripples as well. So I'll come back to this interesting spatial distribution of the bedforms in a bit. But first, it's nice to try and understand the process interpretation for what form these bedforms. And what's really nice is that we can use laboratory experiments to help us understand the bedform formation. One way we can do that is to use bedform phase diagrams, which I'm sure most people are familiar with. An example here is shown on the left by Van der Berg and Van Gelder. And that basically shows different bedform types, where they are stable, depending on the y-axis, which is a mobility parameter, kind of shows flow strength, against the x-axis, which is a non-dimensionalized particle size parameter. So these bedform phase diagrams are really useful to try and understand the flows that produce the bedforms. And the work of Bass in 2016, where they made these bedforms under transitional flows, also produced a bedform phase diagram, and that's shown on the right-hand side here. So I'll spend a bit of time going through this because we're basically going to try and populate this bedform phase diagram over the next few slides. So on the y-axis, we have the mobility parameter, which you could kind of think of in terms of turbulent forces in the flow, or sort of flow strength. And then on the x-axis, we have the increasing yield strength within the flow, so the cohesive forces in the flow. The green area shows where different current ripples were found to be stable. The dashed lines show the different types of transitional flow. And I'm sorry that it's in acronyms because that makes it even harder. But I don't think you need to worry about what the flows are. You just need to know that as we move from left to right along the x-axis, we have increasing cohesive forces in the flow, and we start to produce turbulent modulated flows until we get to quasi-laminar plug flows where we have no movement. So what I should stress is that this diagram was populated by Bass et al. In 2016 by the different bed forms they produced. But I didn't want to show that straight away because it's a bit of an information overload. They will kind of go through the different bed forms we found in the field and see where they fit within this bed form phase diagram. And we can be quite confident that we can use laboratory bed form phase diagram for our natural flow, our natural bed forms we see in the field, because the balance between the turbulent and the cohesive forces should also control the properties of natural sediment gravity flows in their deposits. So starting first with sandy current ripples. The sandy current ripples in the field are very much comparable to classic sandy current ripples found in the laboratory in both their texture and size. You can see that classic current ripples are expected to form below 20 millimeters high and less than 200 millimeters long. And our bed forms were 11 millimeters high and 141 millimeters long. The bed form phase diagram on the left-hand side shows where sandy current ripples formed under mixed sand mud flows that were decelerating. And we found, or the laboratory experiments found, that sandy current ripples formed under mixed sand mud flows with a low yield strength and quite a wide range of grain-related mobility parameters. And they basically formed under flows which were fully turbulent, so they formed under turbulent flows. Moving on to large current ripples. The large current ripples in the field are definitely comparable to the laboratory large current ripples in their mixed sand mud composition, their size, they're much larger than sandy current ripples. Other textural things we saw, such as the muddy base, the high angle cross lamination. And in the laboratory, large current ripples formed under the same range of mobility parameters as sandy current ripples, but of flows that had higher cohesive strength. And these flows were interpreted to behave as turbulence enhanced transitional flows and lower transitional plug flows. And these were the flows where you increase the clay concentration, but you also increase the turbulence near the bed, because you've added another shear layer by this development of a plug. So that can help us understand why these ripples are larger, because we have enhanced near bed turbulence, which is able to erode the bed more and make the sediments, make the bed forms larger. Finally, the final bed forms we saw low amplitude bed waves. The low amplitude bed waves in the field match their laboratory counterparts in their shape. They are very long and quite thin, and also in their composition. In the field, we found low amplitude bed waves that were mixed sand mud and also just pure sand, and that was also found in the lab experiments. And they also both have low angle cross lamination. So again, looking at the bed form phase diagram, we can see where the low amplitude bed waves were found in the lab, with the area that's highlighted. So these bed forms formed under flows that had really high cohesive strength. So they were considered upper transitional plug flows. And these are flows where, because you've got so much clay and you have a really big plug layer, you have attenuated turbulence at the base. And basically this makes these really long, thin bed forms because they just can't grow any higher. So this is all of that put together. So just to briefly summarize this again, when we have flows with low yield strength, we produce sandy current ripples, typical of classic current ripples. As we increase the yield strength, we start to produce turbulence enhanced transitional flows and lower transitional plug flows, and these produce the large current ripples because they have enhanced turbulence at the bed. When we go to really high yield strength values in the flow, we have really thick cohesive flows which have a plug which goes almost down to the bed, and here we can only produce low amplitude bed waves. So the laboratory experiment showed us that there's a really nice and clear link between the bed forms we find in the field and the flow properties. So this can lead on to how we can use bed forms to infer flow processes. So I'm going to say it again, I feel like I'm really trying to hammer this message home, but in the laboratory, when we increase clay concentration, we change the flow dynamics and we move from turbulent flow via transitional flows to more laminar flows. And this in turn produces sandy current ripples, large current ripples, and low amplitude bed waves. In the field, we actually see we see the following pattern. We see sandy current ripples followed by large current ripples, followed by low amplitude bed waves when we're looking at the dominant bed form type in the field. So going back to those pie charts, we can see that sandy current ripples are most common near Aberystwyth, and then in the middle sections, large current ripples dominate, and then at the most distal parts, low amplitude bed waves dominate. So our knowledge of the link between the bed forms and the flow behaviour and the observed changes in bed form type indicate that the flows transformed as they travel through the fringe to the distal fringe of the fan. I guess we should say that we see a variety of bed forms observed at each location, but this just implies a variety of flow behaviour reaching different locations. But the main trend is that we seem to see flow transformation from more turbulent flows to laminar flows, from the fringe to the distal fringe of the fan. And that's summarised in this figure here. So if we start off looking at the A, which is kind of a schematic diagram of the fringe to the distal fringe of the fan, so from Aberystwyth to Borth, we see increasing mud contents in the deposits, and then the little schematics for ripples show the order in number of different types of bed forms we see. So in the most proximal location near Aberystwyth, we have sandy current ripples are the most prevalent bed form type. Second most is low amplitude bed waves, and then large current ripples are the least prevalent bed forms in that area. Moving to the middle section, we see that move around. We see large current ripples become more dominant and low amplitude bed waves, and we start to see reduction in the normal sandy current ripples. In the most distal part, we see low amplitude bed waves dominate, some large current ripples, and no sandy current ripples. So then looking at B and what this kind of means for flow transformation, we can see that the link between bed form type and flow behaviour allows us to imagine how the flows change throughout the system. So near Aberystwyth, turbulent flows mostly dominate, although because we see examples of other bed form types, we also know that other flows are there as well. And then as we move through the system, our change from large current ripples to low amplitude bed waves suggests flow transformation to more cohesive flows. So it's interesting just to do a sort of thought experiment for what is making this change in bed form type, dominant bed form type, and the flow behaviour. So the trends in dominant bed form type suggest the flows become more cohesive from Aberystwyth to Borth. And it's interesting to think of how that changes the flow dynamics in terms of the Rationale number. The Rationale number is a really useful parameter to think about the flows. It describes the ratio of inertial to viscous forces. And the equation is shown here. It's calculated from the depth average current velocity, the flow height, and the apparent kinematic viscosity. And when we have a high Rationale number, we have turbulent flows. And when we have a low Rationale number, we have laminar flows. So we need our Rationale number to reduce as we go through the system from Aberystwyth to Borth, so kind of from the fringe to the distal fringe. So the Rationale number is already pretty low. And we can speculate that it's probably quite likely that the depth average current velocity parameter in this equation reduces distally because the flows are depositional. As we lose sediment, the density difference driving the flows reduces, so the velocity reduces. We don't see huge amounts of evidence for deep erosion in our sedimentary logs or in the outcrops, so we can be quite confident that the flows are mainly depositional and are losing sediment. However, what we do know is that a large amount of mud is carried to the distal fringe. So we have really thick mud caps in the most distal part at Borth. So this means that mud is carried along for the whole time. So then we can speculate that the apparent kinematic viscosity probably increased because of the shear thinning nature of clay flows. So we reduced the velocity, and that allowed the clay minerals to collide and flocculate and start to actually increase the viscosity of the flows. So our clay concentration doesn't really have to change, but just the slowing of the flows increases the cohesive forces. It's really hard to anticipate how the flow height might have changed from the rocks, but again, we can kind of speculate that it's pretty likely that the flow height was either constant or reducing. It would have reduced from the deposition of sediment. Lab experiments and models have also shown that when flows become more cohesive, mixing at the surface reduces. And then finally, although this is thought to be a confined system, there is also still the possibility that lateral spreading of the flows might have somehow reduced the flow height. We're not really sure how confined the system was completely. So if we put those all together and say, okay, we have a constant or decreasing flow height, we know we have flow deceleration, and we're quite confident we have an increasing flow viscosity. This means that as the flows traveled from the fringe to the distal fringe of the fan, the Reynolds number would have reduced, and this would have promoted the flow transformation and explain our observed trends in dominant bedform type. So I've spoken so far kind of quite focused on our field sites, but I just want to say that we really think it's quite likely that there might be mixed sand mud bedforms in other deep marine systems. We know that transitional flow deposits and hybrid event beds are common in the distal parts of other mud-rich deep marine systems. And these are produced by transitional flows, so therefore it's likely that mixed sand mud bedforms are present as well. And we don't necessarily need to constrain ourselves to mud-rich deep marine systems, because hybrid event beds and transitional flow deposits have also been found in the distal parts of sand-rich systems. So if mixed sand mud bedforms are present in other deep marine systems, these could be a really useful indicator for the outer margins of submarine fans. This can be an additional tool to help you work out where you are. What's also really neat is that maybe assemblage of different bedform types could help you determine to an even more precise location where you are within the fringes of other deep marine systems. So if anyone feels inspired to go and try and find these bedforms, or thinks, oh, maybe I've seen something like that before, we've made a kind of crib sheet, if you like, of how to identify these different bedforms based on their texture, their dimensions, and the style of cross-lamination. We were really spoiled in the Aberystwyth grits and Borth Mudstone formation because the rocks are just very clear. It's really easy to see these detailed sedimentary structures. This might not be as easy in other outcrops. But if you have an understanding of the range of bedform sizes and the angle of cross-lamination, that should be hopefully enough to help you distinguish between sandy current ripples, large current ripples, and low amplitude bed waves. And I'm just going to finish with an interesting observation we made at the kind of distal fringe of the area in regards to hybrid event beds. We often found mixed sandstone mudstone bedforms present in the base of sequences that resembled the hybrid event bed model of Horton. The only difference is that instead of having a massive sandstone as our H1, we had these mixed sandstone bedforms. This is quite important for the interpretation of the flow behaviour that produced these beds, because it means transitional flows are interpreted to form the H1 of these mud-rich hybrid event beds rather than high-density turbidity currents. This isn't anything, I don't think, too radical, because there's actually been a lot of work showing that there's a real variety of hybrid event bed types in the natural environment. And if these mixed sandstone mudstone bedforms are found below hybrid event beds in other systems, this suggests that maybe when we interpret hybrid event beds, we can start with transitional flows as the base. So to conclude, I've shown you laboratory experiments which have shown that clay can promote the development of transient turbulent flows with complex depositional properties. Previous lab work had shown that transitional flows could produce mixed sand mud bedforms that were different to classic sandy current ripples. We went out to the fringe of the mud-rich deep marine system of the Aberystwyth grits group and the Borth Mudstone formation, and we identified these novel mixed sand mud bedforms. We found both large current ripples and low amplitude bed waves. Large current ripples are interpreted to form beneath transitional flows with enhanced near-bed turbulence, whilst low amplitude bed waves are interpreted to form beneath transitional flows with attenuated near-bed turbulence. The down-dip trend of dominant bed form type from sandy current ripples via large current ripples to low amplitude bed waves suggests flow transformation. And we can be confident of that because we are confident of our link between bed form type and flow behaviour. We really think it's possible and probable that large current ripples and low amplitude bed waves are likely to be present in the fringe of other deep marine systems, and that hopefully these bed forms can be used as additional indicators for the outer margin of deep marine systems, and assemblage of these bed forms might allow you to really pinpoint where you are. And with that, I'll take any questions. Thank you very much.
Thanks for that, Meg. Really interesting talk, and it's great to see, so many wonderful pictures of the field when we're all stuck in. Well, some of us still stuck indoors. So thank you for that. Whilst you're typing questions into the chat, people, just to let you know that once we have the forums back up and running, you'll be able to put your questions in there as well. So if you're watching this on a recording, please note that there will be an opportunity for you to ask questions in our forums when we have them up and running, so that we can keep this conversation going on for as long as we need to. So yeah, I'll start with some questions now then. And when you post your questions, if you could say where you're from as well, that can help as well. It's had a well done from Yako. First question then is from Emma Morris, who asks, who says, "Hi Megan, thanks for a great talk. Have you noticed any differences in the distribution of bed form types with relation to local features such as channels, or are these observations only noted in the lobes?" And that's from Emma Morris from UCD.
Oh, thanks. Yeah, that's a really good question. So we think, we know we're in the fringe to the distal fringe of the system, and it's very hard at the Aberystwyth to kind of follow individual beds along. So I have to say we haven't noticed that, but maybe we haven't looked for it as well. So that would definitely be something that would be interesting to consider.
Next question's from Mazos, Mohammed from Saudi Arabia. Thank you, Megan, for a very informative webinar. I just wanted to ask, what are the cohesive forces that usually operate on a flow?
Sorry, could you say the last part of that question?
What are the cohesive forces that usually operate on a flow?
Okay, so the cohesive forces are mainly related to the clay mineral type and the clay mineral concentration. So I showed that if you increase the clay concentration, that increases the cohesive forces. We also know that different clay minerals have different chemical and physical properties, which controls kind of how cohesive they are, how strong they are. So if you have a very strongly cohesive clay, that will make the flows more cohesive at a fixed volume concentration compared to flows which were maybe composed of a weaker cohesive clay mineral. I think work is just beginning now on kind of the role of biological cohesion in sediment gravity flows. So the sort of sticky stuff that biology produces can also help increase the cohesive forces in the flow.
Cool. Next question's from Zinshan, who says, "Thank you for the great talk. Is it possible to meet transitional bed forms like long, thin bed forms in floodplain or fluvial environments?"
Yeah, that's a really interesting question. And that's actually something I was just thinking as I was making up this presentation, that we haven't really explored that very much. And I think basically wherever you get kind of high density cohesive flows that are depositional, you could potentially form these bed forms. So yeah, it'd be really interesting to see if they are found in other environments. Sorry, I don't know is the answer, the short answer.
Okay, that's why we do science. Next question is from John Raymer. He asks, to what extent will sand grain size play a role in the distribution?
Oh yeah, that's a really interesting question actually, because we don't see much change in, we don't see huge changes in sand grain size now that we're already at the fringe to the distal fringe of the system. So I think sand size obviously affects bedform height and length in pure sand flows. And maybe if I was going to start speculating wildly, I would say, okay, so our, in our large current ripples and our Lancashire bedways, which are kind of more sandy than they are muddy, we do see some which are kind of, especially the Lancashire bedways, which are sand rich. That might be important. But yeah, I think that's a really interesting question. And maybe I'll think about it over the next few days and send an email if I have anything more insightful to add to that.
Great. Next question is from Jagby, who says, great talk. Earlier you mentioned about conducting Markov chain analyses on these bedform types. What was the outcome of it, and how did these bedform types stack vertically?
Okay, so sorry, that was me not being particularly clear. We conducted Markov chain analysis on the different facies we saw, one of which was mixed sand mud bedforms. So that was kind of just to show the common facies associations, such as hybrid event beds or I don't know, Balmer style sequence. I suppose it would be really interesting to try and do that actually. I think because Markov chain analysis is really dependent on the number of counts you have, you would need a lot of bedforms to get something manageable out of that.
Yeah. Next question is from Gillian App, saying, such an interesting talk, thank you. You talked about bedforms forming slower in mixed mud sand bedforms. Can you elaborate? Is it an order of magnitude slower?
Oh gosh, I'm not sure I can remember how much slower it is, but I can definitely send some papers that show it. Yeah, it really does significantly reduce the bedform development rate when you have clay both within the bed or within the flow. But as to actual magnitudes, I'm afraid I can't answer that off the top of my head. And I'm aware that there are people in the audience who definitely can. So maybe they can add something to the chat.
Great. John says he's looking forward to your email, and thank you for the talk.
Gosh, thanks.
Great. So we'll just give it a couple of minutes. Okay, we have another question just come through. Question from Dominica Chiarella, saying, thanks for your talk. How did you evaluate outcrop exposure versus ripple migration? I assume some of the exposures were not exactly parallel to the flow, and this might impact the height and length that you measured. So did you apply any corrections?
Yeah, so we use kind of flutes and grooves to, when present, to kind of understand, yeah, if we were looking at the bedforms in kind of the right orientation to measure lengths and heights. And yeah, we applied corrections to make sure that was dealt with. Great.
Cool. Well, I'll just, if anyone else has got a question, get it through now. Oh, Yako's helping. It says 1 order of magnitude slower development for clay, more for biological polymers. So hopefully that will answer Jill's question.
Thanks, Yako.
Great. So yeah, if anyone's got any more questions, just post them quickly, and we'll get them sorted. If not, forums will be up soon, so we can continue this conversation, which would be fantastic. But for now, we're really pleased to have had so many of you here. So thank you so much for coming, and we're really pleased to have had you here, Meg. So thank you very much for standing in and giving such an excellent presentation. So hopefully we'll see you all next week, where we're going to be having a talk from Jaroszewicki, the University of Colorado, who's going to be talking about the advent of the Anthropocene epoch. So I'm really excited for that, and I hope to see plenty of people there as well. So in the meantime, please come to one of our Seds Online coffee breaks if you'd like to just say hi or hang out or talk about sedimentology. I know that the Australasia group has got a schedule of things to talk about. So go and have a look at that. That's on the website. That's on one of our newsletters that we sent a couple of weeks ago, if there's anything you want to particularly talk about. So yeah, fantastic, and hope to see you all at an event very soon. Thanks again.